Okay, welcome back, dear students. In today's class, we'll be dealing with red-black trees, the second approach, that is top-down insertion. Before moving to this point, let us recall what we have studied in bottom-up insertion. So in bottom-up insertion, this is also known as ordinary binary search insertion, where the insertion of a new node always takes place at the leaf node. And then we have to follow the BST properties. So we'll first insert the node at the leaf node, then we will check out what is the criteria for red-black tree, whether it is satisfied all of the properties, whether they are being satisfied or some of the properties are violated. If some of the properties are violated, then we need to do rotations and then recoloring. In all of the cases we have studied in the last lecture. Okay, so this is most easily done recursively. In bottom-up approach, we can do recoloring and then changing the nodes by doing some rotations. This is done recursively until all of the properties are satisfied. Insertion winds up the recursion on the way down to the tree to the insertion point. In bottom up, we move with the leaf node till the root node. We check all of the points, all of the sub nodes, meanwhile fixing the tree as the recursion unwinds. Now in top down insertion, here we will first insert the node in top down fashion, and then we will do corrections if some of the properties are getting violated while traversing down to the tree to the insertion point. So this is exactly opposite as that of bottom up approach. When the actual insertion is done, no further corrections are needed. Here we have a benefit of this. We further do not need to again check again and again whether properties are being violated or not, since we are checking this while traversing down to the insertion point. So we do not need to traverse back up the tree here in case of top down insertion. So this can be done iteratively, which is faster than the previous one. Now the goal of top down approaches, insertion is always done at the leaf. As like ordinary BST insertion will take at the leaf node only, but here the way of traversing down to the tree is from the root node, that is from the top. Now recall from bottom up approach flowchart that if the uncle of a newly inserted node is black, we restore the red-black tree property by 1 or 2 local rotations and recoloring. We do not need to make changes further up the tree. Therefore, the goal of top-down insertion is to traverse from the root to the insertion point in a way that red-black properties are maintained, and at the insertion point the uncle is black. That's why we may have to rotate and recolor, but not propagate up the tree back again. Here we have possible insertion configuration. See here, when you insert a new node at X, this can be, if a new node is inserted as a child of Y or Z, there is no problem since the new node's parent is black. When you insert at either Y or at either Z, you further extend its branches, then there will be no issue because both of the nodes are colored here black. If a new node of Z, if we insert a new node at this node Z, then there is also no problem, since this will be at the time of new insertion, Z will become the parent of the new node, and it satisfies the property that parent will always be black. So here the color of Z node is already black. So if we insert a new node at this point, then there will be no issue. But if the new node is inserted at Y node, further we extend a branch of Y either to left or right, then there's no problem, since the new node's uncle is black. New node's uncle, see, the new node inserted at Y whose uncle is Z, and Z is black here. So with a few rotation and recoloring, this insertion can be done. If the new node is inserted as child of Y or Z, look at the color of Y and Z node here. Since both of them are red, parent is also red and uncle is also red here. We'll have to go back up to the root of this, up to the parent of these two nodes. That means we have to back trace the tree. We have to trace up one level to this tree to find out which case is getting violated here. Now see here, we have a figure to the left. As we traverse down the tree and encounter this case, see the case we discussed just now. Y is a leaf node and Z is also a leaf node. Here, if we insert the new node either to Y or Z, then we have to look up to their parent. What is the color of the parent? And we found that the color of parent is black. So there are three cases here. Remember, here we have a goal to create an insertion point at which the parent of new node is black or the uncle of the new node is black. Since it doesn't satisfy this goal, so we need to do some computation here. So in this case, we will just recolor both of these nodes where we want to make insertion. So we'll recolor Y as well as Z as black, as shown in the figure. You can. Now here, at this point, this is the extension of the tree. We have to look further in this case. Now, X parent is red. So here we'll have to check the grandparent's color. X parent is red. X is the parent of Y and Z, and X parent is P, and the color of this parent is red. And X and P are both left and right children of the grandparent G here, right? So P and U, these are the children of G, where P is the parent of X and S, X is the parent of Y and Z. Okay, so here we need to rotate, need to do some rotation. So rotate around G. Considering these three here, we will do some rotation and then color P as black. After doing rotation, you need to color P as black and then color G as red. Now note that X uncle, that is U, X uncle, since X parent is P and uncle is U, must be black because it was initially black and would have been made black when we encountered G. When we encountered G, it would have been made black. So which would have two red children, X parent and X uncle. So here these must be recolored. In this case, see, we'll try to understand this with the help of diagrams. See, this was our scenario. After recoloring and rotation, what happened? We rotated, right? So we considered these three in rotation And we know the property of rotation, that the middle node becomes the root node, whereas the parent becomes the right, if we are doing rotation in the right direction, right side. Okay, and this will become again the left child. So here P becomes the parent, X becomes the child of P, and G becomes the child of right child of P. Okay, I hope you are following this. So this happened after rotation, and then we recolored G as red and satisfying the property. Now here we have the third case where X parent is red, so grandparent is black. So X and P are opposite children. In that case also you need to rotate P around G and then change the color of P and also change the color of G to red. Make P as black and G as red. Again note that X uncle must be black, that we already have seen what are the criteria for the uncle to be black. Let us see how this has taken place. This was our scenario earlier when there is a raise of case 3. At that point we did some rotation, right? So now look here, we have P is the parent of X, right? But X is a right children of P, not the left children. Okay. So in this case we'll have to rotate in this direction. Are you getting this? We'll make a rotation using these 3 nodes. We'll do the rotation with these 3 nodes P, X and Z, and here we will do rotation towards the left side. So X will become the root here, P will go to the left, and Z will become the right of X, right node of X. See, this is shown here. This is step 1. Then you need to recolor X, Y and Z and then rotate around P, right? So after doing this we get this. Now again there is red conflict here. So parent and children node cannot be of the same color. So here the property is getting violated. In order to resolve this conflict or this problem, we again have to rotate. Now here we will be rotating X around G. So taking into consideration these 3 nodes and doing rotation towards the right side. So X will become the root node, P will become the left and G will become the right node. And we will recolor G as red since G is now the children of X. So X will be recolored as black because X becomes the root node here. I hope the concept is now clear to you. Here in one go I have shown all of the 3 cases. What is happening here in case 1? If P is black, just recolor it. We are doing it just recoloring the X. If P is black, we are just recoloring the X, Y and Z as shown in this top figure. In case 2, P is red and X and P both left and right child, then we have to perform some rotations here. Okay, so rotate this. First you need to rotate recolor X, Y and Z and then rotate around G using P as the middle node. So the final diagram you are getting here is to the right side diagram. In case 3 again, okay, alright then, we'll see this with an example. See, now here we have the values. Now we will be considering the values instead of labels and we'll try to satisfy the BST property, and also we will check the red black property. See now, 15 is the root node. The BST property says that the root node, whatever value at the root node is there, the right child should have the value greater than the root node, and the left child should have the value less than the root node. So here the property is satisfied. 15 is there as the root node, 10 is the left child, which is obviously less than 15, and 70 again, which is greater than 15. Then further at 70 you have further child nodes as 20 and 85. So here now this is okay till then. If you have another node to be inserted, which is 60 here, then and problem is what? See, in red black tree property is getting violated. We know that here we have a conflict. As we further add a new node to 20 as right child of 20 as 60, then we know there cannot be two nodes, parent and child node cannot have the same color. So in this case we'll have to do recoloring, and this is shown in the third figure here. See, 20 and 85 are colored as black, and then because the property is again getting violated, now parent node should have black color. So it was in black color, right? But black color is only for the root node, since 70 is not the root node here. And if this 20 and 85 are the children of 70, then 70 should be black. Okay, fine. But here the property was getting violated, right? So we have to recolor this 70 as red. And after that you'll have to check the values. Now after that, if you have a point where you have a new node to be inserted as 30, so 30 being greater than 20, this will be the place for insertion for 30, okay, and then 60 will be to the right side. Then at this point it is okay with this. Next, if you have another node to be inserted as 50, then you'll have to find out the location where you can insert 50. So we found that at this node 60 we can further extend 50 as its left child. But then again you have a conflict, red conflict. So then you need to recolor it. Okay. So we did the recoloring of these two nodes as black, right? But then if these two nodes are black, then obviously the parent of this should be changed. So we changed it to 30. But then again a new situation arose. 70 and 30 are getting here a conflict. They are having the same color, red conflict. Okay. To resolve this, we need to perform rotation towards the right side using these nodes. Okay. So using these three, I will have to do some rotation. So after rotating it to the right, 30 will take place of 70, 70 will go to the right side, and 20 will be the left child of 30. And this is how the figure looks like. Now after doing so, because we didn't change the color yet, there is again a problem of red conflict. So here we will be doing again rotation using these three. Okay. Now we'll need to perform rotation towards the left side. So using this three, the middle one, that is 30, will become the root node. 15, as it is less than 30, will become the left child, and 70 will become the right child, and hence we'll get this diagram. And now it is satisfying the property. See, this is how your red black tree looks like after resolving all of the properties that are getting violated. I hope you have understood this. Recall the rules for binary search deletion. Now let us have a look at top-down deletion. As we know that deletion is not so easy in red black tree. No doubt we are deleting the value, but we are keeping the node as it is. And we are shifting, we are replacing the value of that node. So if a node to be deleted is a leaf, then we can simply delete it. But if a node to be deleted has just one child, then in that case you need to replace it with that child. That means if it is the middle one and it has one left or right child, then if it has only one child, then you will be replacing that node value with the child value. Okay. In case 3, if a node to be deleted has 2 children, again one more complexity added here. It has 2 children. Then replace the value by its in order predecessor value, then delete the in order predecessor after taking recursive steps. Now just think about it, what can go wrong here? If delete a node is red, if you are deleting a node whose color is red, then you will not face any problem and no red black properties will be violated. But if the deleted node is colored as black, then in that case you have to perform a check. If the node is not the root node, see, we have many cases where a node can be black. The first most important case is the root is always black, right? So if the node you are deleting, it is black, you have to check out whether it is the root node that you are deleting. Then there will be major changes, right? If not, that means if the node is not the root node, then deleting it will change the black height along some path. If you are deleting a node which is not the root node of the red black tree, then obviously, but the color is black, huh? So obviously there will be a change in the black height along some of the path, either left path or right path. So the terminology here is X is the node being examined. You are examining, in this example, the example we are taking here is, we are examining the node which is labeled as X, and T is X sibling. Okay, that means here X is one node, another node is T, and both are siblings. That means they are having one parent which is called as P. We are labeling X and T's parent as P. R is the right child of T and L is the left child of T. Okay. Now the strategy that we are applying here is, as we traverse the tree, we change every node we visit X to red. As we go down from top to bottom at the point X, we examine every node, and if there needs to be changed, then we change them along the traversal only. When we change X to red, we know that P is also red. X parent is P, right? So when we are proceeding towards X point, we came across the parent of P also, the parent of X also. Parent of X is P, which is colored red. So if we are changing the color of X to red, then there will be a problem. So, right, if we know that the color of parent is red, the children's color cannot be red at that point. Okay. And T is black. T is the sibling of X. So P's children are X and T. Since P is red, its children is black. Now step number 1, examine the root node. If both of the root's children are black, make the root node red. Here you need to take care of this. if a root node, if any left subtree or right subtree, the basic thing is that the root node is always, the main root node is always colored as black. Look at the root node's children. If the root is black, then children must be colored red. Then move X to the appropriate child of the root and proceed to step 2. Otherwise, designate the root as X and proceed to step 2. If there is no root node, then you have to designate X as the root node and then carry forward. Step 2, here is the main case. As we proceed down the tree, we continually encounter this situation until we reach the node to be deleted. The situation is X is black and P is red and T is black. We know the situation, P is the parent of X and T. So we are going to color X as red, then recolor the other nodes and possibly do some rotation based on the colors of X and T's children. Here in this case, we have X, we are taking this case as 2A. The case is X has 2 black children, and 2B is the case where X has at least 1 red child. So let us first examine case 2A where X has 2 black children. Look at this figure. Here X is a point where it is having 2 black children, and X parent is T, which is colored as red, and uncle of the child of X is T, that is X is having one more sibling, T. Now we have one more case here, case 2A1. In this case 2A, we have further 3 cases. T has 2 black children. Here in this case it doesn't have, but if in some situation it has 2 black children further, then case 2 we need to examine if T's left child is red and if T's right child is also red. So if both of the T's children are red, we can do either of these two cases we can consider. Now let us see case 2A1, that is X and T have 2 black children. See, look, X and T both are having 2 black children here, right? So in this case we know that if children are black, then parent cannot be black. So we will just recolor them as red, as you can see in the diagram, and then we move down to the tree. In second case where X has 2 black children and T's left child is red, look at the situation which is shown in the figure here. So here in this case you need to do some rotation. We need to do rotations here. See, these are the null nodes. There is no value here but a null pointer. So rotate L around T. You need to rotate L around T and then L around P. After doing this rotation, T will become here, right? T will be here, L will be at the place of T, T will go right, towards the right. Okay, so here L will become here. Then we will rotate it around P. So obviously P will go to the left side. Doing this rotation, the node P will shift to the left side of L. L will become the root node. Here you can see what has happened after doing these 2 rotations. So now L become the root node, P is its left child, right T is its right child. Now here we further recolor X and P and then continue down to the tree. We'll further change the color of X and P and then proceed down to the tree. In case 3, your X has 2 black children and the right child is red. If this is the scenario, then what you need to do? Rotate T around P. First you need to do this rotation, taking these 3 nodes P, T and R, perform rotation towards the left side. So T will become the root node, P will become the left child, and this X position will be shifted down one level. R will become the right child of T, and you will get this kind of tree. Then you need to do recoloring. But since X was colored black, you have to change the color of X, P, T and R, and then proceed down to the tree. Now in case 2b, where X has at least one red child, then simply continue down the tree to the next level. If the new X is red, then continue down again. If the new X is black, where in case T is red and P is black, then you need to perform some rotation. Rotate T around P and then do recoloring of P and T. And back to the main case, you'll have to check out for step number 2. So doing so, you'll get this kind of diagram which is shown here. You'll be moving down to the tree. See, if move to black child to B, then you need to rotate T around P and then recolor P and T, and then go back to step 2. If you have moved to the red child, then move down to the tree. Okay. Now step number 3 is finally find the node to be deleted. Finally you will find the node to be deleted. That is the leaf node or a node with non-null child. That is a leaf node. Then delete the appropriate node as a red leaf. And step number 4 is color the root as black. Now here we will take an example to better understand this by taking some values over the node. So see here, in this case you have root node as 15, whose left child is having value 6, right child is having value 17. So till here it satisfies BST property. Now if you proceed further to the left subtree, taking root as 6, so here again it is balancing the property. Left child is 3 and right child is 12, which is greater than 6. Then further moving this, we have 12 as the root, and left child is 10, right child is 13, then 10's left child is 7. So till now here it is satisfying by a BST property. Again here the values are balanced and it satisfies the property again. Now step number 2, where root has 2 black children, where root is having 2 black children, then you need to color the root as red and descend the tree moving X to 6, right? So here we encounter that value, okay, it is satisfying the BST property, but what about coloring? It is colored as black. So root and children cannot have the same color, right? So here we need to change the color of 6, as well as we need to change this color as red, and then move down to the next level. Okay, so see, here is your X, okay, and we had changed the color of the root node, okay, because if we go on changing the color of these two, then more changes will have to do. Okay, so one of the X children is red, case 2b example is there. Now children is red, then you need to descend down to the tree, arriving at 12. Now since here x, that is now x becomes 12, we are proceeding down to the tree and we are marking every node we are visiting, we are marking it as x. Okay, so now we move to 12 and now this is your x. Since the new node x is 12 and it is colored as red, your case 2b1 need to be followed, and we'll continue down to the tree, arriving at 10. Okay, I hope you are following me. Then since 10 is the node to be deleted, here we found 1 that we want to delete the node. So now whatever value we want to delete is the 10, the node we want to delete. Simply we need to replace its value by its children, since it is having only one child. So we'll remove this 10 from here and we'll replace the value with 7, and this 7 value will be replaced by null. And then finally we need to change the color. When we have replaced it, since it was having different color, right? 7 was having a color as red, but we need to color it as black, because now 7 takes the place of its parent. Okay, then trees with constant update time at a known location. When we are updating the trees at constant time interval, we are updating the trees, and that too at a known location. Now here the insertion and deletion operation along the tree, rearrangement and recoloring are performed in log n time. The time it takes to rearrange the nodes and recolor them will be log n. Insertion will take place OL, and if the location is already known to us. So here we have ended with this topic. See you in the next class.